Have you ever stopped mid-sentence while counting or doing quick mental math and suddenly realized that the phrases we chant out loud make absolutely no grammatical sense? If you grew up in India, Pakistan, Bangladesh, or any nation heavily influenced by the vintage British colonial schooling system, you definitely remember standing up in a crowded, noisy classroom, sweating under a heavy metal ceiling fan, and shouting out multiplication tables at the top of your lungs. We did not say 3 times 2 equals 6. No, that took far too much breath and completely disrupted the collective rhythm of 40 children trying to stay in perfect auditory unison. Instead, we sang out 3 twos are 6, 4 threes are 12, and 5 fours are 20. But what on earth is a, ja, za, or za? If you open any authoritative English dictionary from Oxford to Merriam-Webster, you will never find this mysterious mathematical operator listed alongside addition or division. It sounds like a strange alien language or a piece of modern internet slang, yet it has been the foundational building block of math education for hundreds of millions of students across multiple generations. The real origin story of this phrase is a fascinating mix of linguistic evolution, colonial history, the physical limitations of human speech anatomy, and the universal human need for rhythm. To solve this linguistic mystery, we have to travel back in time over a century and a half to 19th century British classrooms. Before modern electronic calculators, digital smartboards, or interactive learning apps existed, the primary method for teaching children basic arithmetic was rote memorization through collective chanting. British headmasters and teachers did not use the phrase times because it felt disjointed when repeated dozens of times in a row. Instead, they taught multiplication tables using the plural form of the numbers followed by the verb are. For example, a child in a London classroom in the year 1880 would stand up straight and recite 2 twos are 4, 3 twos are 6, 4 twos are 8, 5 twos are 10. When you speak this phrase slowly and deliberately, it sounds perfectly normal and grammatically correct. 3 twos simply means 3 groups of 2, and they are 6. However, classrooms are rarely places of slow, deliberate speech. When an instructor forces a room full of energetic young children to repeat these lines over and over again at high speed to build muscle memory, the human tongue naturally takes massive shortcuts to save energy, breath, and time. This is where the magic of phonetics and speech blending, scientifically known as corticulation, comes into play. Try saying the phrase 3 twos are 6 out loud as fast as you possibly can 10 times in a row without stopping. Very quickly, the hard, buzzing Z sound at the end of the word twos naturally collides and merges with the weak vowel sound of the word are. In English phonetics, when a sibilant consonant like S or Z hits an open, unstressed vowel like the A sound in R, they fuse together into a completely new, singular vocalization. Twos are rapidly compresses into tuzar, or tuja, or tuza, or tuza when the British Empire established its formal English medium schooling systems across the Indian subcontinent and other colonies. Local teachers and students adopted this auditory chant. Because they were learning by listening to the fast-paced rhythm rather than analyzing the individual words grammatically on a page, the blended sound of twos are was written down in the mental notebooks of millions of children simply as ja, or za, or za, or zar. It was a classic case of a massive, multi-generational phonetic mishearing that worked so perfectly it became an official part of the cultural landscape. But this phenomenon did not survive just because of a simple misunderstanding, it survived because it is a brilliant hack for human memory. The human brain is hardwired to remember patterns, beats, and musical rhymes far better than dry, isolated facts. Chanting 3 to the 6 turns a boring mathematical equation into a punchy, staccato, double-beat musical lyric. It creates a rapid-fire cadence where every single syllable hits a specific beat. This structural rhythm allowed entire classrooms of children to stay perfectly synchronized without anyone falling behind or breaking the momentum. If a student had to pause and articulate 3 times 2 is equal to 6, the extra syllables would destroy the collective flow, trip up the tongue, and slow down the mental processing speed. By shortening the verb phrase into a single, explosive syllable like the table gains an unstoppable momentum. It transforms abstract math into muscle memory, allowing children to recall multiplication answers instantly, almost like the lyrics to their favorite song. However, this structural adjustment to speech patterns is not unique to English-speaking regions or colonial history. Human beings all over the planet have independently realized that abstract mathematics must be transformed into music if you want a child's brain to internalize it forever. Let us look at how other global cultures solved the exact same speed and processing problems. In India's indigenous vernacular education systems, long before the widespread adoption of English medium curriculum, mathematical tables were memorized through deeply poetic structures in local languages like Hindi. Take the phrase "teen duni chhe," which means 3 multiplied by 2 equals 6. The words aren't just dry labels, they follow a strict lyrical format where duni means multiplied by 2, tia means multiplied by 3, and chauke means multiplied by 4. When recited sequentially, it sounds like an ancient rhythmic song rather than an administrative drill. It completely strips away all filler words, keeping the math incredibly fast, tight, and mentally sharp. Moving further east, if you think the Tujia system is fast, the traditional Chinese method takes processing speed to an entirely different level. They use a system called the Zhu Zhu Ji, or the 9-9 song, which dates back over 2000 years to the spring and autumn period of ancient history. The Chinese language possesses a massive mathematical superpower because its numbers are entirely monosyllabic. When a child in China learns 3 times 2 equals 6, they do not say words for times or equals or are. Instead, they say exactly 4 short syllables, san er delio, which literally translates to 3 to gets 6. For equations involving higher numbers, they drop the verb entirely, meaning 3 times 3 equals 9 is spoken simply as san san zhu or 339. This turns multiplication into a rapid-fire computer code running inside the brain at maximum velocity, optimizing the human mouth's output efficiency. On the complete opposite end of the spectrum, we can examine languages like French, where the numbering system itself functions as an intense historical and mathematical workout. In French, the number 80 is not its own unique, independent word. It is spoken as quarterwinks, which literally translates to 420s. If a student wants to recite an equation resulting in 97, they have to say quarterwink diksh sept, which literally means 420s, 10, and 7. Trying to chant that complex linguistic formula in a fast-paced multiplication table requires immense cognitive pacing, showing that the specific language you speak deeply shapes how your brain visualizes and structures basic arithmetic. When we analyze these global systems side by side, we see a universal truth about human cognitive biology. The brain is not a cold, digital calculator designed to store isolated lines of data points. We are fundamentally creative, pattern-seeking, musical creatures who interact with the world through cadence, meter, and rhyme. The reason the Tuja system has persisted across generations, long after the British Empire withdrew from its former colonies, is because it perfectly aligns with how our working memory operates. When an abstract numerical concept is tied to a distinct rhythmic beat, it bypasses the slower, analytical parts of our conscious brain and drops directly into our procedural memory, the same area of the brain that remembers how to ride a bicycle, tie a shoelace, or play an instrument. You do not have to consciously calculate what 3 times 6 is because your brain recognizes the acoustic shape of the phrase 3 6 ja 18 before you even have time to visualize the numbers. By shrinking a clunky, multi-word grammatical phrase into a single, punchy, explosive syllable, millions of school children successfully hacked their own biology to optimize their learning speed. Therefore, the story of 3 2 6 is far more than just a funny quirk of broken English or a relic of colonial classroom conditioning. It stands as a living, breathing piece of cultural and linguistic synthesis, an intuitive optimization engine disguised as an accidental mishearing. It proves that human beings will always find a way to turn the driest, most difficult academic tasks into a high-speed melody that stays locked in our minds for the rest of our lives. Thank you.